Welcome back. We've been learning about the cell membrane, and we want to focus in on the processes that are involved in moving materials from outside the cell to inside the cell and back again. And that always has to do with the concentration of materials due to the random movement of materials, bouncing of these molecules, bouncing off one another and off surfaces. There's going to be eventually a movement of materials from a high concentration to a low concentration, as you see pictured here. And so they're going to move from a high concentration, where there are many of these molecules, just by the random collision of molecules, they're going to be moving over to a low area. We'll come back to that in a moment. Okay? Now, we refer to this typically as passive transport, where no energy gets involved, just the random collision of molecules as they move from one side of the cell membrane to another. And this is going to occur as very small molecules that you see here are able to migrate just right across the phospholipid bilayer. And these are typically going to be very small molecules that are usually nonpolar. Some of them are very small and slightly polar as well. So we refer to that as passive transport. And there's basically two types that you're going to look at. We're just going to refer to normal diffusion here when we see very small molecules that are typically nonpolar or just very slightly polar. And then there is the movement of water, which is what osmosis is. Osmosis is always going to be referring to good old H2O. That's going to move fairly freely inside and outside of the cell. Now, there are basically two types of transport that we see, but they're always going to be moving down a concentration gradient. Well, what do I mean by a concentration gradient? Well, if you've ever taken any type of food coloring or ink, perhaps in art class, and you put some drops of that into the water, you'll notice that eventually the color is going to spread out and diffuse. If you give it enough time, it's going to spread out and equally color the solvent, in this case water, through there. And that's what we mean by a gradient. If you want to look at it another way, materials are going to be initially introduced perhaps in a higher concentration, but eventually due to the random collision of those molecules, they're going to be moving to where they aren't, or to where they are in very few numbers. So we refer to that as going down the concentration gradient. In other words, if we refer to this kind of as a hill, this would be high on the hill and this would be low on the hill. All right? Now, when we focus on water, that has its own name, but basically it works on the same principle. Materials move from a high concentration to a low concentration. And osmosis here is going to refer specifically to the diffusion of water. And when we refer to that, there's basically three types of solutions. When we compare them with the concentration of materials in the cell. When we take a look at this first illustration, there's basically a balance, an equilibrium, as it were, between the concentration of molecules outside the cell and those that are inside the cell. And so if the concentration of dissolved solutes in and out of the cell is roughly the same, then we've reached a dynamic equilibrium where there are roughly the same amount of dissolved solutes in and out of the cell. And so the movement in and out of the cell of water is going to be about the same. A second case here is going to be when there's a hypertonic solution. Hyper comes from a Greek prefix which means high or over. And again, the principle of diffusion still applies, but in this case, there is not a balance of dissolved solutes in and out of the cell. The solutes are in higher concentration outside of this cell, hence the prefix hyper. But what this means is that the concentration of water, of the solvent, is low. And so water is going to move from a high concentration, in this case it's going to be inside the cell, and that's going to move outside the cell because that's where water is in lower concentration. And so you're going to have a net removal of water leaving the cell. And this is going to lead to a net decrease in the volume of the cell that you see pictured here. So that's going to cause cells to shrivel up and be smaller, even die in extreme cases. A practical benefit of hypertonic solutions, however, is if on a day where you have a stuffy nose, you can go down to the corner drugstore and pick up a nasal solution that's hypertonic, and temporarily, if you spray that up in your nose, that's actually going to cause your nasal tissues to shrink temporarily and giving you a greater ability to breathe. Now, the opposite is actually more dangerous, hypotonic solution to the cells. Let's say that cells, for some reason, get exposed to distilled water, which is 100% H2O. Well, that means that the water outside of the cell is going to be in very high concentration compared to the solution that's inside the cell, where there are a variety of dissolved solvents. There's a variety of dissolved solutes inside the cell. And so in that kind of situation, water is going to be in lower concentration inside the cell than it is outside the cell. And so we refer to that as hypotonic because there's fewer solutes, and yet because the concentration of water is lower inside the cell, that's the direction the water is going to move at the end of the day, what we call the net movement. Water is going to be leaving the cell, but more is going to be coming in. And so you can see pictured here, the cells are actually swollen and can even burst because there's relatively little that this particular cell can do to prevent water from continuing to enter in, and then the cell has burst. There are some cells, however, that have structures inside of them that can actually pump the additional unneeded water out. All right, so I hope that's helped. So that means that iso means same. The concentration of the solutes in and out of the cell are roughly the same. Hyper, the solutes that are dissolved in the solution outside of the cell are higher than what you'd find inside the cell. And hypotonic is just the opposite, where the amount of dissolved solutes in the water are lower than what you would find in the cell. And again, this is going to be the most dangerous situation. And then some molecules can diffuse only through the help of transport proteins. And these are molecules that will not easily pass through this phospholipid bilayer. Keep in mind, these tails that you see inside the cell membrane, these are nonpolar, and so that means that there are materials that either cannot wiggle through that tiny space, or they're going to be strongly polar or even ions. And as you know, these nonpolar tails will not interact very well at all. It's just like trying to mix water and oil. They're not going to interact. They're not going to blend in. And so ions such as potassium and calcium that you need, for example, for muscle contraction, they're not going to be able to get in and out of the cell. So they're going to need help. And so there are these wonderful proteins that are embedded into the cell membrane, transport proteins that you see pictured here in the blue. These are going to help these unusual molecules to get across the cell membrane. Now, there are a limited number of these, and so in a very high concentration gradient where there's a very big difference between the inside and outside of the cell, these can get overwhelmed, kind of like, you know, the checker at the grocery store when there's a big crowd or a big sale going on in the cell. These can get overwhelmed in a high concentration difference, but normally they work just fine. helping these unusual particles, such as glucose, across the cell membrane. Well, listen, thanks for watching. Bye-bye.